The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Okay. I guess I'll start now since I think this might be the crowd since most people are probably sleeping after the sprint submission deadline. Were most people up at 6 a.m.? Most if not all. All right, so my name is Cory. I'm from the winning team last year. And what I really want to do today is kind of give a complete information dump. So this lecture will almost seem like a stream of conscious, but these are the things that throughout all of our years at Battlecode are the things we really wish we had got in lecture but never actually got. So my goal is hopefully to give kind of the most relevant, hopefully like the most applicable lecture to the nitty-gritty details of like the day-to-day things that you're doing in Battlecode in order to make your bot better and try to improve your performance against the other teams. So whatever competitive edge you can glean from this, hopefully propel yourself to the top of the ladder. So just to give a little bit of background about myself, I've been in 3 teams since 2010. The first 2 years were kind of meh, but in 2012, we were finally able to win the entire thing with my teammates, Yanping, Haitao, and Justin. And each year was quite different because of the people you work with. So what I want to do is give a lot about our 2012 experiences and kind of explain the various choices we did, the tricks and techniques we did in order to give ourselves an edge over the other team. And I also want to give special thanks to these 4 teams in particular: Gunface, My Archon, Died Bellman, Fording the Stream, Drunkosaurus, and Toothless. Just know that like Battlecode is not done in a vacuum, and you learn from all the other teams. And so these teams were particularly helpful that our team learned from, that our team collaborated with, that we were able to share code bases and learn from each other, et cetera. So just to preface everything, we're the ones, Fun Gamers is the one responsible for the spec this year. So if any of you guys have problems with it, you can't really blame Max or Steven, you have to blame us. So any cries for like nerfing, OP, whatever, it comes to us. We made a lot of huge changes this year just because we wanted to mix up the game a little bit. And also we wanted to make it a little bit easier for people to start off code bases and get running players. I don't know how many of you guys played in 2010 or even 2011, but the amount of code required to get even a simple bot up and running was enormous. So in 2010, because you couldn't actually attack a unit until you had equipped a gun on a robot, it took almost like 1 to 2 days worth of code base before you could even get a robot moving and attacking simultaneously. So what we did a lot was simplify a huge number of things to make it a lot more higher level strategic control. So no walls, attacking is completely automatic. We removed directionality. I don't know how many of you guys played last year, but this one's like pretty big. There's no robot directionality. We added in shared vision, global broadcasting, and node map. So do most people enjoy these changes? Or at least people who have played it in previous years? Yeah? We're really excited, at least, about, in particular, having the map completely known and the global broadcasting, because it allows like an unprecedented level of robot communication this year. So you can now, instead of having a bunch of almost completely autonomous robots with very limited broadcasting, you can now coordinate attacks. You know the map. You can design your strategy based on the map rather than wandering around for 100 to 1,000 rounds, not knowing where to go, getting stuck behind voids, et cetera. The no walls is also very interesting. What we found in previous years is contestants will sometimes just, if the map is really stupid or really retarded, what will end up happening is you just watch for 3,000 rounds, both people stuck in their base because of this like really interesting concave of walls that prevents the people from getting out and actually engaging each other. So with no walls, you can actually basically control the battlefield. You can defuse mines, you can add your own walls, you can prevent your enemies from attacking. You can like create kind of, you can bend the battlefield to your will, which we thought was really exciting, especially because you're no longer completely screwed over if the map wasn't what you expected. So to begin, I want to emphasize that Battlecode is a trade-off of time. So this is like, this is what Battlecode ultimately comes down to. You have 3 to 4 weeks to basically implement an entire bot. Okay? And in these 3 to 4 weeks, you have to decide what is most important. If you spend your time on the wrong thing, you will not win. You have to spend your time where it matters. And in particular, I want to say that results to effort vary very highly between what you choose to spend your time on. So one of the most important things to spend your time on is attack micro. If you can win every engagement, you will win the game. It doesn't matter if they're higher level strategy. If you always win the engagement, you will beat their army straight up no matter what. Okay? Next is swarm code. If your swarm moves together, you will usually win the engagement. If you have better swarm code, your attack micro can be a little bit off, but you'll still end up engaging with larger numbers and winning the fight. And winning fights wins games. The navigation code allows you to actually get to the enemy swarm and defeat them. And then there is some high-level strategy that you can't make completely wrong choices. But once again, if you have good attack micro, you can make questionable high-level strategies, but still win every engagement. So the way I'm going to structure this lecture is I'll have various tags. There are certain things that apply to novices. There are certain things that apply to advanced players. And then there are certain things that apply to expert players. This also comes down to a trade-off of time. If you have 4 people, maybe you want to consider doing some of the more advanced tricks and tactics. But if you only have, say, if you're working solo or you only have 2 people, you want to spend your time where it matters. So don't spend time implementing things that give you very tiny marginal advantages when you could, say, be focusing on your attack micro and win all the battles rather than saving maybe like 1 or 2 byte codes per iteration. So the first off, to do well in Battlecode, you really have to know the spec. And I know we've been really bad at keeping the specs up to date, and there have been typos, but hopefully by now, everything has mostly been standardized and corrected, and all the typos. And then you guys didn't really like our diffusion joke, so we changed the word defusion to diffusion so that you guys didn't think it was a typo and we were stupid. So quick quiz. What's the base spawn rate? Someone call it out. 10. All right, nice. What's the cost for 3 suppliers? Cumulative. What was that? I think I heard it over there. 60, right. Because it starts off with 10 for the first supplier. Then the cost is additive. So 20 and then 30 into 60. 60 total cost for 3 suppliers. What is the spawn rate with 3 suppliers? It's 8. So total cost of 3 suppliers is the spawn rate of 3 suppliers is 8 per round because it is kind of a curve. The first supplier will get you down to 9. The second supplier will get you down to 8. And the third supplier is actually the first supplier that doesn't bring you down another point because it's rounded to the nearest integer. Even. So in terms of unit spawned, at what round does the first supplier break even? So these are all critical numbers that if you know, you can kind of game the spec to your advantage. Close. The first supplier breaks even at what round? If I get 1 supplier, I have 1 turn spawn reduction, which means I break even in terms of units at what round? I sacrifice 1 unit to get the supplier, so I'll break even when I get back that extra unit, which is at 90 rounds. So the first supplier breaks even at 90 rounds. So these are key numbers. They may be tweaked in the future, but if you always have a sense of all these numbers, you can kind of make good high-level decisions about what you should be building and what you shouldn't be building at the beginning of the game. So the beginning of the game is very key. What we did was you have an excess of energy. So you have a choice, like in Max's lecture yesterday, of whether to build generators or suppliers. And if you know roughly at what time these things break even, or at what time you gain the marginal advantage, you can decide when to attack or when not to attack. So know the specs. That's very key. Second, I want to say testing is probably the most important thing, second from spending your time in the correct place. Because you don't actually know if you're spending your time in the correct place unless you're actually testing the code. So as a high level, you want to write multiple distinct bots. So I know a lot of teams maybe just have like a single bot lineage, but our team, we wrote like 10 to 12 different bots, each one with like different strategies. And sometimes we wrote bots completely from scratch when we thought we had a really cool strategy. So last year, there were like flying units. So we thought, well, it would be kind of cool maybe if we could have units that only, or if we had a base that only spawned flying units. And we did a little bit of theory crafting in our head, and it turned out the DPS was like marginally higher. But the problem is, once we tried to implement it, we found out the actual problems with the flyer strategy was that we couldn't sustain the units because of the way that energy transfer was done last year, and we weren't actually able to coordinate the attack well enough to gain that theoretical DPS. So testing is extremely important. Wins, of course, beat theory crafting. So you can, even knowing the specs and knowing the breakoff times, you have to be able to implement them in practice, otherwise the theory doesn't pay off. The scrimmage server is your ally in testing, and then you always want to prioritize writing behaviors over spending a lot of time doing framework code, because the behaviors are what you're actually testing, not the framework. One thing that novices make the mistake of is they're always afraid of ranked games. So has everyone in here played at least one ranked game? Yes? So what I want to say is it's really a problem more with novices than with the people who've been doing Battlecode for a long time. And the reason this is because sometimes you submit a bot and you're afraid that it's maybe not so good, or there's some problems with it, or that your code is going to do badly and you're going to lose points. But what it gains you is by scrimmaging often, you will always know what the top teams are up to. And the thing is, if you do unranked, top teams actually have no incentive to accept your match, and you'll never know what they're actually doing. So the trade-off is a top team, if they beat you in a ranked game, they'll actually gain ELO points. But you actually gain something from that. You gain the understanding of how the top team is microing, the kind of high-level strategy the top team is doing, and also any tips or tricks or small things that you can glean from those games to perform better in your next bot iteration. Actually, if you send an unranked game to one of the top teams, it's actually a lose-lose situation for them, because A, they have the probability of losing a lot of points to you, and B, they're also giving away their high-level strategy. So for the top like 5 teams, at least in years past, if you sent them an unranked match, they'd cancel it and send you back a ranked match, because there's almost no advantage for them to accept these ranked matches. So don't be afraid of sending ranked games, especially against top teams, because that's where you're going to learn the most about how you can improve your bot. Another thing that sometimes beginners get wrong is that your code base is actually more than your bot. There is a huge infrastructure that we built, at least around our bot last year, that was not just the simple, that was not just robot player and everything surrounding robot player. So one of the easiest things you can do is you can make custom maps. Every year, when we start Battlecode, we always make this map on the right. We call it planes, because there's absolutely nothing on it. The planes for this year, we have like a few encampments in the middle just to test like basic encampment capture code. But what planes really allows you to do is it allows you to perfect your attack micro and make it so that you're not worrying about like advanced pathfinding. You're just making sure you can win engagements. Because as I said, like attack micro is so important. Winning engagements wins games. So spend time actually making custom maps. I know we don't really have a map editor out this year, so if you make like a map editor too, make a bunch of custom maps, test your pathfinding, test your attack micro. There's so many small things you can do to test your bot very fast. A few small things that you guys may have also not known is with custom maps, you can actually declare units to be pre-spawned on the map. So in the top right, you're allowed to declare symbols. You can actually set up unit formations to quickly test different scenarios. And just by hitting play and repeatedly running it, you can tweak whatever heuristics you're running in order to make sure that your code is actually running correctly. And then making custom maps is also extremely good for testing pathfinding. So you can spawn a map with a unit already in the center, and then just hard code in an endpoint to nav to, and then see if your navigation is running any better than it was before. This is kind of like a little bit expert thing, but we spent a lot last year trying to game the scrimmage server a little bit. So Justin wrote kind of a scraper that scrapes the rankings every 5 minutes and determines who's winning to who. If you guys are just starting out, don't worry about this too much. But what this allowed us to do actually was it allowed us to know which teams were actually rising quickly, which teams had maybe changed their strategy, and it allowed us to kind of target our ranked matches, because we would see, oh, this team won like 3 games in rapid succession. We want to see what they're doing. Or, oh, this team maybe like dropped 4 games, and we probably don't really need to send them a ranked match because they're probably not doing anything different than what they used to be doing. But once again, this is a custom tool that was written outside of the framework of just our Eclipse project with our Battlecode bot that allowed us to gain like a small competitive edge over everyone else. This, the current ladder stats ranking system is actually, I think Justin posted about it in the forums. He's actually running it publicly for you guys this year. So if you want to take a peek and just use his code. Our old one actually recorded ELO gains and losses, so we could see like whether a team like gained like 1 point or whether they gained 10. So if a team gains like 30 points in a single match, that's like a warning bell, right? Because it means they're doing something drastically different, and you want to know what they're up to. This tool was another tool we borrowed from Gunface from 2011. It's basically a mass scrim tester. So the scrimmage server actually is not the only place that you can mass scrim. You can also build your own custom mass scrimming framework, which is what Gunface did in 2011 and what we co-opted from them in 2012. So what this actually allows us to do is it allows us to test in-house our own bots against each other. So you know how I said we wrote like 10 to 12 distinct bots? What we would do was we could actually characterize which one was strictly superior to all the other bots by pitting them against each other in thousands of matches. So if you'll see here, what this did was we had a total win counter, so we could submit jobs to our queue server. The queue would run like 50, 60 matches on every single known map in the scrimmage ranking. And then, of course, it'd take some time to compute. We borrowed a bunch of XVM machines to continuously run this in the background. But you'll see here, every single one of our tagged releases, we're actually pitting it against each other. Last year, we would consider a bot good if we could beat our older iterations like 90% of the time. And until we could get kind of that 90% mark, we would consider them about to be equal, because some small change in maybe like the random number generator or whatever would affect the outcome of the match. But again, the most drastic improvements, when you see like 31-0, those are usually from micro improvements, where one bot will just, the 2 armies will collide and one bot will just obliterate the other one, even with equal numbers. But these sort of things, running the mass scrim, you can really get a sense of. This is an expert level kind of thing. If you have one person, you're not going to blow your time writing like a scrimmage-based system. But if you have maybe 3 or 4 people, you could take a day or so to maybe try to repurpose the old 2012 mass scrim tester, which is on GitHub, by the way, to get it working with the 2013 game. One thing that hasn't really been covered ever, I think, is kind of the bytecode system in detail, I think, in Battlecode. And this is a very key part of Battlecode, and yet it's always kind of glossed over. You'll hear like the lecturers say, you should use less bytecodes, or like the less bytecodes you use, the more units you can have. But what does that actually mean, and how does that actually translate into implementation? So I'll skip ahead and just give a brief overview of the JVM for people who are unfamiliar with it. So the Java virtual machine is a stack-based system. So what it basically means is, if you're familiar with x86 or whatever, there are no registers. There's just a giant stack. And you can imagine it as values get pushed on the stack and popped off of the stack, and that's how computation is done. Bytecodes are, when you write your Java, it gets compiled into something called bytecodes. And bytecodes are very similar to assembly, except they work on this stack-based system. And the way the stack is you have this operand stack, which is your current stack of values. So if you imagine like prefix operations, I can push, or postfix operations, I can push 2 values onto the stack. I can call add, and it would pop off the result, right? So if you imagine the JVM is kind of working like that, it's very similar, but there's also an array of local variables up top. And these are indexed by number. So actually, stack operands can operate directly onto the array of variables that are globally accessible. And then there's also a global constants pool that bytecodes can operate on. So this is just an example online. And if you want to read more, there's a URL down here. But what happens is you compile your Java. It gets turned into bytecodes. And then each bytecode is actually stepped through by our instrumentation engine. And that's what you're getting counted on. So when someone says you're using like 10 bytecodes, it actually means that the high-level Java call you made is being turned into 10 individual atomic steps on the JVM. And you're getting penalized for each one of these atomic steps. This leads to a lot of interesting things. So there's a very classic kind of loop structure in Battlecode. I hear this is so classic, actually, that Dropbox's code base is littered with this structure. So it looks like kind of a normal for loop. But if you look closely, you'll notice that we don't even have a third parameter. What this is it for I is equal to the length of the array, decrement until you're greater than 0. And it's reversed from maybe like the way normal computer science would teach it to you. But there's a particular reason we do it this way. And that's because we're actually bytecode hacking. So what happens is Java is similar, kind of like there's legacy in that in computers, testing against 0 is actually an operation that comes up very often. In most branch conditions, you're testing against 0. Like Booleans are testing against 0, et cetera. So there's actually a special bytecode for testing against 0. And then also, when you're doing the comparison, you don't want to be recomputing, say, messages.length every single time. So this actually has a net effect of saving bytecodes, because you can't actually write the bytecodes out, but you can predict what the compiler will spit out. And because Battlecode is not run as just-in-time compilation, actually, the bytecode is stepped through exactly as it's outputted. This ends up with a net savings of a few bytecodes. So if you'll see down here, this is like the classic way you would write a loop that you might learn in Intro to Computer Science. For I is equal to 0, I is less than your terminating condition, increment I. What happens here is because you want to compare I every round to messages.length, computing messages.lengths is actually a separate compare operation with loading the actual object, loading the actual array object. Whereas in our initial version, what we've done here is we've set the index variable actually to the final value, and we're comparing against 0, which is a single bytecode operation. So what happens is that this is a net savings of like 2 bytecodes. Okay? 2 bytecodes actually might not seem like a lot, but if you're, say, looping through 100 objects, that's 200 bytecodes saved in the entire loop, and that's 2 whole sense functions. So you could sense that's 2 whole like global sense functions with the radius and the location. That's actually pretty big. So saving 200 bytecodes can mean that you might have additional data on the battlefield, or you can loop through 1 additional object when you're trying to compute a heuristic for map locations or for army positions. And this actually gives you like a small marginal competitive edge over the other team, especially this year when bytecodes also translates to energy. So saving bytecodes gives you back more energy. More energy translates to more units. If all your units are saving like 500 bytecodes per turn, that adds up over time, especially with the decay rate. So with bytecodes, you'll also end up wanting to implement your own data structures. So I don't know if you guys have tried using the native Java data structures like hash set, array queue set, et cetera. But we actually penalize you for the internal calls that Java makes in those data sets. So if Java likes to be very safe, so a lot of the thread safe code will like check to make sure like another thread is not trying to mutate the data, or that there's not a lock on the data, et cetera. So the thread safe code actually ends up hurting you a lot because there's a lot of excess bytecodes that gets called. So for instance, a single hash set.iterator.getNext, getting a value from a hash set, worst case is 2K bytecodes for a single call, which is absurd because you can implement a hash set yourself with an array and maybe like 200, 300 bytecodes if you custom write it. So what ends up happening is a lot of people will make what's called fast data sets. So we wrote like a fast hash set, a fast array list. And these were all custom based on arrays that we could index directly into and pay a very minimal bytecode cost in order to get very complex data structures back. Same thing goes for algorithms. You may think that a lot of beginners will start off trying to implement something like A* or a flood fill algorithm just to do navigation. Yes? Right. This is an example from our. I'll explain what exactly this one is. But just as an overview, like most n-squared algorithms are completely untenable on the bytecode system. So if you see an n-squared algorithm, it's not going to work unless you do something to it. So there are multiple ways. You can distribute it among multiple robots, which is actually very hard. You can break up the computation into multiple steps and run a piece each turn, which is hard depending on the algorithm. And then you can also just run a completely different algorithm. So the one I actually have up here, this is a cute little example from our old code base. It's not the actual implementation, but it's the algorithm itself. This is called a multiply with carry. It's actually a pseudo random number generator. There's a period. There's like a period of like 2 to the 60th, but for all intents and purposes, it is a random number generator. We actually implemented this because we noticed that math.random on seeding pays 144 bytecodes, and then each subsequent get next integer call is 80. And we actually wrote our own custom random number generator to save 40 bytecodes per call to get next int. And so this is the algorithm actually pulled from Wikipedia. We changed it a little bit. But in essence, it's a bunch of bit operators that gives you a pseudo random number generator to save on bytecodes. And if you have an algorithm that relies on a lot of random numbers, the 40 per get next integer actually adds up. There's actually a tool, a really nice tool that we used a lot last year called Dr. Garbage Visualizer. I don't know why it's called Dr. Garbage, because it's like one of the best tools ever. But what it does is it decompiles your class into the actual bytecodes, and then it shows the control flow graph on the right. So the control flow graph will actually allow you to reason about where your short circuits are happening, because if you short circuit a code block, you're not actually paying the bytecode for what you don't execute, right? So you'll want to terminate loops early. You'll want to try to avoid code that doesn't have to be computed multiple times in order to reduce your total bytecode count. So by having the control flow graph on the right, it's actually very easy to reason about how to save bytecodes, especially when you'll see the control flow graph plus the instruction plus kind of a small comment about what the variable is or what the method call is or what the constant is. So that's enough. So ultimately, with bytecodes, the last thing I'll say is, if you're not sure, test it. We give you a function called getBytecodesNum, and this allows you to see what bytecode number you're currently executing. So if I want to, say, profile a particular function call I made or a particular algorithm, just surround it with system.out println getBytecodeNum. And this will tell you the total number of bytecodes that your algorithm took to execute. And you can use this to kind of profile it down. You can try different things, but ultimately, whatever gets that number smallest is what helps your bot when you're optimizing algorithms. We actually, at the bottom, this is a little loop this is a little function call that I've added at least every year. At the end of every robot's round, it actually checks the round number and the current bytecode number to see if it went over bytecodes, and will actually emit a warning to the system console that it went over bytecodes. So actually, it's really annoying, but it's really helpful if every time a robot goes over bytecodes, it yells at you, because then you can play a match. If you're not actually like profiling if you're not actually explicitly saying that, you can sometimes ignore it because the bytecode number is just in the top right of the client, and you'll kind of miss it sometimes. You'll see like, oh, maybe it's like 10K, but like whatever. But if like your robot is yelling at you every time it goes over 10K, and your entire army just like screams in the middle of the battle, there's something that has to be changed in order to make it so that you're not missing an attack, or you're not missing a movement every turn that you could be moving. So this year, actually, it's even more critical because there are no cooldowns. Every robot, every turn can move. So if you go over bytecodes once, that's a lost movement. which could translate to a lost attack. So it's very critical in battle situations that you do not go over bytecodes so you can get your movement. And I'll show you why a bit, especially in micro situations. So micro is really important, attack micro. I've been emphasizing this over and over. You should know the execution order of the robots, or you should know what happens when. So when attacks happen. So when do attacks happen? At the end of the round, right. You should understand like kind of the discrete nature of the map, and you should know that micro is better than everything else. So I don't know if Max has covered this, but in 2 robots, which robot actually wins the 1v1 engagement? It is, yes, it's the one who closes the gap first is the one who wins the engagement. So if I have 2 robots 2 squares apart, right now it's a stalemate. But if red makes the mistake to move in, what happens is blue closes the distance and gets the attack off first. And all things being equal, red will attack second, but blue has already done the initial damage, which means on blue's turn where he kills red, red will not deal back the corresponding damage to kill blue. Blue will win, so blue will have 1 more robot in the next upcoming engagement, and therefore higher DPS and will win the next battle. This situation is also particularly bad because red can't actually retreat. If red moves back, blue can still close the gap next turn. So understanding kind of how the micro works in this game is actually very key to winning engagements. So in a 1v1 situation, the gap closer always has the advantage, just straight up. So you will want to write code that takes this into account so that you can actually win engagements. In a 2v2 situation, it's a little bit more complex. So what happens in 2v2? So red can move forward. Blue can close the gap, but red can close the gap with the second unit, and now he's dealing twice the DPS that blue has, and will eventually win. Blue can actually, if blue is clever, blue can actually micro to focus fire on a single unit because damage is split evenly across all enemy robots. So blue can actually try to micro a little bit to kill the bottom red unit if red makes a mistake, but red will actually can move down and continuously attack blue until the blue robot is dead, and the 2v1 will win. And if red micros correctly, he won't lose a single unit. So in a large fight, or in larger fights, the larger army has the advantage given correct positioning, because you could assume in this sort of scenario, blue can actually reduce this to a 1v1 fight if red does not make the correct choices in the subsequent like 5 or 6 moves. So blue will move up and attack red and reduce it to a 1v1 scenario unless the red robot can retreat backwards while still attacking blue towards the bottom red unit and continue fighting so that they can turn the 1v1 into a 2v1 engagement. So these small like discrete steps are what you should actually be thinking about when you're writing microcode. It's very critical that you don't get indefinitely kited. Like it's very critical you do not write code that ends up in this scenario where you're attacking and then you try to retreat, but you can't actually retreat in this game because the opponent will close the distance. So there's only 2 scenarios in which you can retreat. You can retreat if there's an army behind you willing to back you up, or you can retreat if you're retreating over a mine that gives you more DPS. So there's some team dynamics things that I just want to cover. This is mostly geared towards the novices in the room. But make sure you guys are using source control management. I think this goes without saying. Every MIT class now emphasizes the importance of source control management. And I'll even say you should just use hosted source control management. So if you're using Git, if you're using Mercurial, you should just throw it up on one of these like free hosted SCMs just because you don't want to deal with like the server going down. So my first year, we made the terrible mistake of hosting our own SVN server on an XVM machine from SIP-B, and then like randomly there was some downtime that was uncontrolled, and then we didn't have access to our code base for like 2 days. This was terrible. So just GitHub, these guys are like paid to keep your source up, okay? So SIP-B is not paid to maintain that your Battlecode source does not go down. So trust these large source control guys, and especially trust distributed source control if you guys are familiar. I think Max gave a lecture on Git. So use it effectively. And also figure out your SCM, your source control strategy. So this is actually a big one. Every team does their kind of release cycle, or I would say release cycle, but you're like releasing bots a little bit differently. So I'll explain the way we did it. We had a single package called ducks, just because we really like ducks. Don't ask. We fork off a bot every time we release it. So in our mainline ducks package, when we get to a state, we're saying like this bot's reasonable, we want to submit it to the server. We'll actually copy the ducks package, rename it to our kind of bot naming scheme, which is based on SC2 AI levels, if you guys play StarCraft. And so we started off with medium player. So we'll copy the ducks package into the medium player package. And what this allows you to do is always have a copy of the medium player in your repository, so you can always pit your mainline bot against any of the other heads you've cut off from the repository. So some teams like to do it differently. I know Gunface in 2011 liked to use source control tagging. So what this allowed them to do was they could update to any version in the source control, and they could recompile it. But the issue with that is if you update, you have to update your entire mainline package backwards. You have to recompile it, and then you have to keep the class files around so that you can pit them against your current bot once you re-update to the current head. This gets a little bit annoying, and for us, it was just simpler to persist like 30 or 40 copies of the same file just in different packages, because it saves on time. It's not elegant, but elegance doesn't really matter that much when you're trying to finish a bot in the short amount of time that you have. We actually went one step further. This is technically part of the custom tools, but we actually had a one-touch deploy system. So we had a single script that was responsible for building the release, tagging the release, testing the release on our automated mass testing system, and then cutting the branch from mainline and pushing it back to the repository. This is very key, actually, if you're doing what some of you guys may have been doing last night and trying to submit like 20 seconds before the deadline. Because if something goes wrong, you're completely screwed. So if you have a tool that you know works and you know roughly the amount of time it takes for it to work, it's standardized and you're less prone to human error. So we ran the script, everything's done, we have a jar, we upload the jar, we're done. And this is reliable, that we're not like manually trying to create the zip file. I know some people have been having issues with like bots randomly exploding, or like sometimes a submission works or sometimes a submission doesn't work. If the whole thing is automated, it's going to work, barring some catastrophic failure. This is also a random cute little chip. Sorry for the stream of conscious, but just trying to like mind dump as much useful information on you. This one, I'm actually really surprised. I couldn't figure this out for like 3 years. How to deal with like shared debugging. So for those of you guys working in teams, you'll have like print lines, you'll have indicator strings that like one day you'll be like testing something and you'll merge in someone else's pull, and then you'll be like, who overwrote my indicator strings? Because now I don't know what I'm debugging. Have any of you guys had this issue? So you'll have like, you're like debugging nav, and you're like printing out the current nav state, or your current state machine's navigation position, and all of a sudden like the guy working on attack micro has overwrote your indicator strings with like current number of robots like attacking you or whatever. And this gets like really frustrating really fast, because then you end up with merge conflicts when people try to like change each other's indicator strings. Like the guy working on nav will comment out the attack guy's indicator strings, and then you'll end up with a merge conflict, and then you guys will screw up the merge conflict, and stuff will just like go to hell. So what we did was the bots can actually read from the Java bc.config. And actually what we built was this custom system, this custom like debug system that allowed us to specify who was running the bot based on the current Eclipse launch profile, and only print out indicator strings from the person launching it. So you'll see on the left, like we made 4 custom launch profiles, one for me, one for Justin, one for Hightow, one for YP. And when you ran your custom launch profile, it would only display debug information from your bot. So you'd only see your own print lines, you would only see your own indicator strings, and then we like never had a merge conflict. Well, we did have merge conflicts, but not related to indicator string setting. So this is just like a small little trick that just, it saves a lot of time, because stuff will add up across the across your total bots development time. You don't want to like spend time arguing about people like I know some teams will say like, okay, you can only use indicator string 1, I'll only use indicator string 2, but like someone will need like 2 lines of information, then you guys will like fight over it, and it's like really stupid. Other generally useful advice. all the past teams have actually put a lot of information on, so there's a lot of stuff that I don't need to reiterate. So I don't know how many of you guys actually read the blog post that I put on Hacker News. So yeah, nice. From 2012 to 2009, actually, all the old strategy reports of the winning teams are actually online. So I have the blog post from our team, but there's also a strategy report that corresponds to that, to our bot that's in our repository. The 2011 postmortem is actually an excellent write-up by Steve Arcangeli, who wrote the mass Scrim tester, about various other tricks you can do to save bytecodes. 2010 is by Spencer Skates on finding the shortest path to victory. It's kind of their whole like Bellman Ford pun team thing that they had going on. They detail a lot of like high-level mechanics that help you when you're in combat. Spencer Skates and Steve Bartel also won in 2009, and they were called G2G ice skating lessons, which is, it was like an inside joke that none of us got, but they wrote about their 2009 experiences as well. They actually set the trend of like the winning team usually ending up writing the best strategy reports, which is a trend you guys should continue. Some other random tips. Messaging. I'm really excited about the new changes this year because messaging is global. So what this allows you to do is you no longer have to have robots really close together. So if you guys are familiar with the 2011 game, what you would have to do is, because you could only broadcast 8 squares away, you'd have to send up a relay. You had to set up a relay network of robots that would propagate information outwards. And there's a whole amount of overhead just associated with writing the relay network that could get a message from robot A to your entire army. Like that was like at least a day's worth of work, setting up the rebroadcasting, setting up the hashing, setting up all that code. This year, because everything is a global message board, it makes it easier to broadcast very important information very fast to all your robots. But what this also does is Battlecode has a huge history of message-based attacks. So it also makes the message-based attacks more interesting because now the enemy very easily can see everything you're writing to the board. So some of the more famous message attacks have been, one year, you guys are familiar that the robot VM limit is 8 megs, right? So if you exceed 8 megs, your robot actually automatically implodes. So one year, a team went around just broadcasting 8 megs arrays. So the enemy team would either get it, try to process it, and completely freeze. They'd get it, try to process it, and explode immediately because they like loaded it into memory or something stupid like that. Or they would just stop moving because they constantly exceeded their bytecode limit. Then I think in like 2007, teams were trying to exploit the fixed cost of array.hashcode. So array.hashcode used to be a single bytecode. We used to, there is a package in your distributable Battlecode installer called method costs, and that explains the cost of every single method that we don't explicitly list a cost of, or if a method is not listed in there, it's free unless it's in one of the restricted packages. But what happened was array.hashcodes was free, so teams thought they were being really clever by using the O of 1 hashcode cost to basically do a O of n algorithm to get entire hashcode and secure their messages that way. But then one team just took the fact that every team was using array.hashcode, and he could mutate the array without changing the value of the final hash. And then he would send that back to the robots, and all their robots would just like completely mess up because they thought the hash was correct, but the data was completely garbled, which was like a really interesting messaging attack. So you need to make sure when you're messaging to check the integrity of the data and make sure that the data, check the validity of the data and also make sure that the data actually gets to where it's supposed to go. So this year, the most obvious attack, of course, is to wipe the entire board. And you can do this every round if you have some obscene number of generators, like 30 or so. But the thing is, you can pool energy this year. So actually, a team that, say, just wants to wipe the message board during critical situations, like during an engagement, can actually pool enough energy so that they can wipe the entire message board in one go. So you can't actually assume that what you wrote into the message board one round will actually be there the next round, or even between rounds, because the enemy robot who executed between you could have wiped it. So make sure that whatever messaging scheme you use, there's a way to check the validity. either by hashing and storing maybe like the top 4 bytes as your hash, or by duplicating the information in multiple places and checking that all the information matches with each other. But as long as you can reliably get important information over, like if you have like a retreat signal or like an all-out attack signal, just make sure it's secured and it's safely propagated to all your robots. Here's a random piece of advice. Keep your frameworks lean, especially with the bytecode limit. You don't want to create this beautiful like hierarchy of abstract interfaces that just has like a ton of intermediate layers before you actually get to like the nitty-gritty code. Because for every additional layer of abstraction, you're increasing the bytecode cost. So actually one of the cool things that the bytecode limitation actually enforces is it enforces really lean code, which is not something you typically see in Java. So if you'll actually look at our class structure, this is from our 2012 bot, we have a very, very flat class hierarchy. One, because we just didn't want to deal with extra subpackages. And two, because there's really not too much to be gained from like really elegant architecture other than just wasting time. Because the behavior code is ultimately what matters. So we wrote extremely lean frameworks. So this is actually our main run loop. You'll see here, all we do is we reset our internal timers. We update a few key round variables like the current time and my current energy and the current position of all the bases. And then we run our message system. We actually run this, we run the main run call, which would basically be a giant state machine, probably like 5, 6 to 1,000 lines long of just like completely messy code that determines what the robot wants to do and does it. And then we actually abstracted movement out. This was probably the biggest piece of abstraction that we did, was we moved movement out to a separate position where we knew that each robot was reliably moving every single round, because it's very key that you always move, because that is an impact on your total damage per second. And then we did some generic things, and we also had this cute little thing down here at the bottom, which is if we had some spare bytecodes, we would use the extra bytecodes for computation. So navigation last year was, because there were walls, the algorithms you had to use last year were actually quite different. Most teams would write something called bugnav, which you guys, from the navigation lecture, I suppose you discussed it a little bit, where if you see an obstacle, you hit the obstacle, you try to trace around the obstacle, and then once you're free of the obstacle, you keep moving. But then there's the more advanced teams would actually write a more complex version of bugnav, which is called tangent bug, which is you basically can project a virtual bug, and if you see you've rounded a corner, instead of going forward, hitting the wall, and going around it, you can just cut the corner. And we actually used our extra bytecodes to pre-compute steps of tangent bug in order to make our navigation maybe like 5 or 6 squares better. But that better means you get to the enemy 2 rounds faster because you cut a corner. And then 2 rounds faster means you have extra DPS on the enemy, and so you win that initial engagement. This year, because there are no permanent walls, bugnav and tangent bug may not actually be some of the best algorithms. Haitao and I have kind of a little bet running on what the best nav will be. We're thinking it's probably going to be some sort of very discretized flood fill algorithm, or like A-star algorithm, that doesn't try to compute every square, but actually breaks everything up into discrete segments. So you want to be able to rush to the enemy base if they're just a straight up nuke bot. We guarantee you we guarantee you a minimum of 200 rounds if you follow the optimal path, but you have to know what that optimal path is, or you won't get to there in time. Or maximum of 200 rounds. So our bets are actually on the most advanced teams writing kind of an A-star algorithm or a flood fill algorithm that takes the map, divides it into discrete chunks, so it doesn't consider every individual square, and then it kind of picks sort of roughly the best path to take. So you can avoid areas with more or less mines than the other areas. And then this will still get you to the nuke bot in enough time without having to blow the entire cost of the complete A-star algorithm. So A-star in maybe like an 8x8 or a 10x10 is tenable, but it's not tenable in 20x20 or 100x100 situations. This is kind of a big one. Don't be afraid to write messy code. I think it speaks for itself, but in case you guys are like spending a lot of time like trying to make beautiful code, the thing is, what you ship that changes your bot's performance is ultimately what matters. And a lot of beginners have this issue where they're afraid to just hack something together or hack a one-off bot to test. But it's so key that you kind of overcome this fear to write messy code, write stuff that works, just get something hacked out that's working, and then use that to gain yourself an advantage in what matters, which is the actual scrimmage, the tournament matches, et cetera. So we actually have code that's terrible. Our navigation code actually is completely is not understandable by the person who wrote it anymore, because it's so messy. Like you can imagine BugNav, for anyone who's tried to implement BugNav, it sounds really simple, but there are actually like hundreds or so of edge cases that you have to account for. So if you end up bugging around another robot, or you end up in some sort of infinite loop bug, there's a lot of extra edge conditions that you have to account for that none of the previous lectures have actually like talked about from like 2009 or 2010 or 2011. They'll just say like, oh yeah, it's like BugNav, just like go around the thing. But what happens if you have like 2 units bugging around the same wall and then they hit each other? Then one unit has to go around. But if one unit goes around and the unit on top moves, all of a sudden you have a unit who's no longer next to a wall but thought he was bugging around a wall, but he doesn't see any wall next to him anymore. And then your states get messed up and everything just goes to hell. So don't be afraid to just write edge case code that deals with that, gets your bot up and running so you can test like the frameworks and the strategies and everything that matters. There's also like last-minute hacks actually win games. So I don't know if you guys are familiar with our 2011 or 2012 championship, but what we did was on the very last day we were scrimmaging on the server, and we found out that the second-placed Scrim team, Team 16, had modified his attack code that was actually slightly better than ours. And because having better attack code means you win the engagement, it means he beat our bot actually like three times out of 4. So we got actually really scared about this. And don't forget, we scrimmed this the day of the final submissions. So an hour before the deadline, me, Hightown, YP are thinking about, well, what should we actually do? So our ultimate hack was we actually figure out what the team is by the characteristic of their message broadcasting. So you're not actually given the team number, but if you look at what kind of messages they're sending, you can kind of guess, right? And throughout the whole Battlecode 2012, we had been kind of like on the side, just like curious, like looking at the structure of other teams' messages. And so an hour before the deadline submission, we wrote something that determined whether the team we were playing against was Team 16, and we would change our strategy. And this was like an hour before, and it was completely untested code. But we had been thinking about it kind of in the back of our mind, and we just threw this together, we uploaded it, and if you were at the finals, it was a pretty tense match where we actually had a bug in that code that triggered once and then would not trigger a second time. But the one time it did trigger was like the very last match, and so we ultimately won the final tournament. But this is like a piece of code, incredibly critical. It's like 3 or 4 lines, but it was the difference between like first or second place. So once again, it's like spending time where it matters is like really key. You can probably do these sort of hacks this year. Determining what the team is based on the message structure is a little bit harder, because last year people would send discrete message objects, and so you could count like the total number of integers, the total number of map locations, whether there's like a secret key, and then you could like correlate the secret keys. This year you'll maybe have to see like how they like channel hop, or what they store in the various channels, or kind of like the channel distribution of the different messages, but it's still possible. So last-minute hacks do win games. This is also another small one. You guys should all, if you're not already using IRC, you should use IRC, because all the devs are on IRC, especially us who are remote. I was the only person working on the engine who was actually willing to fly out 6 hours to give this talk. So everyone else is on IRC. If you have any questions, you should go on IRC, and you should actually ask your questions. So for those of you who don't know, there's a web client. Just use the free node web client. Connect to channel Battlecode. Ask whatever questions you have. We'll answer them pretty fast. If you guys are feeling like a little more advanced, you should like use IRC better. If you actually persist in the channel, there's like a lot of banter that goes on regarding game balance, or like teams will like discuss strategies or whatever. So if you actually like get a good IRC client and stay in the channel, you'll actually learn a lot. Because sometimes some of the old Battlecode champions will just come in, just talk a little bit about strategy, or people will just like discuss like what they've been doing on the bots, etc. So just use like a good IRC client. Like if you were to use Pigeon, like Pigeon has a built-in IRC client. There's no reason to not connect to it. Just talk to the devs, ask questions. There's been like a lot of very simple questions, but we're more than happy to answer. So like questions about like round number, or if you have an issue with your bot, it's much faster than the forums because we'll answer the IRC probably in like minutes rather than hours on the forum. And most of all, you guys should just have fun. Like Battlecode, at least for us, was a very fun experience. We worked hard on it, but we also like we goofed off a lot. Like we probably spent more than 40 hours playing Civ 5. And before the sprint tournament, or before like the quals tournament, this is usually a bad idea. But this is like IAP, it's about having fun. So work hard, but also have fun. And also, I have a few requests. So there may potentially be the 2013 winner in this group. So if it is one of you guys, just a few requests. You guys should write a good strategy report, because Battlecode is not done in a vacuum. We learned from the teams before us. The teams before us learned from the teams before them. This information really needs to be more out and open, which is why I'm giving you kind of a brain dump of a lot of the very small tricks and tips that we did in order to gain the competitive edge. So write a good strategy report. Help your fellow competitors. This is a friendly competition. It's not cutthroat. You guys can like make fun of all the other lesser competitions, but within Battlecode, like keep it a good family. And then join the devs if you guys win, because we need good devs. So thanks. So any like general questions or whatever? Once again, yeah, it's our fault if you guys like really hate Nuke. You should say it now. Yeah, yes.
Cory, how did you that you did Battlecode with? I mean, it changed from year to year. So how did you choose your team?
The 2012 team was all Star League people. So there's also another Star League team. Have some high hopes for the Star League guys. First year, I did it with people from my high school. Second year, I did it with Star League people. Third year was all Star League people as well. So you guys should go to Star League if you like StarCraft. That's a pitch. Every Friday, 7 o'clock, 253. Go play StarCraft. It'll make your metagame analysis better. Any other questions? Balance? General comments? So I'll be here afterwards if you guys want to ask any questions. If you want to look through our old bot, at some point I will write up a code walkthrough of our 2012 bot. But until then, you just ask, or we'll be in the IRC channel or whatever. So hopefully this was useful to you guys. So thanks.
Thank you.